Welcome to MetaMinds Academy. In this lecture, we are going to learn vector differentiation and directional derivative. The concept of directional derivative and problems on directional derivative we will learn. So, in coming to vector differentiation, so what is a scalar point function and what is a vector point function? What is a scalar point function? Scalar point function is a function that maps vectors to scalars. And vector point function is a function that maps vectors to vectors. The output is also a vector. So an example of a scalar point function is f of xyz equal to xyz square. You can also write f of xi plus yj plus zk. That means the function f here, it is mapping the vector xi plus yj plus zk to the function xy z square, to the scalar xy z square. See, there are no ijk in this, it is a scalar. Here also the function phi maps the vector xi plus yj plus zk to x sin y plus cos z, and it is also a scalar. As there are no ijk in this, you can easily identify it as a scalar. So what is here xi plus yj plus zk? It is actually the position vector of a point P. You take the xy plane or xyz space 3D. So here you take a point Pxyz in this space. The line, the ray connecting from origin to the point P, is the vector. Of course, ray has no limit, but here we consider the ray from 0 to, that means origin to P only. Origin to the point P. So every point xyz, for every point xyz, you can write the vector r bar as xi plus yj plus zk, which is called the position vector of a point. The position vector of the point P xyz. It is actually OP bar. So for every position vector xyz, there corresponds a point P, xi plus yj plus zk, there corresponds a point P xyz. So instead of writing xi plus yj plus zk, we write simply xyz, because we take xyz from this vector and substitute here in this function. So we can simply write phi of xyz equal to x sin y plus cos z. That is a scalar point function. And what is the vector point function? It maps vectors to vectors. Here you take a vector, you take the position vector r bar, which is xi plus yj plus zk. That means you are mapping this point to another vector, right? Indirectly. So the output is a vector here. xy into I plus sin y into j plus x cos j into k. So what are ijk? Ijk are nothing but the unit vectors in the direction of j is the unit vector in the direction of y, k is the unit vector in the direction of z axis. So what is a unit vector? Its modulus is 1. A bar is a unit, said to be a unit vector if its length is 1. So we take the unit vector in the direction x, as we named it as I. In the direction of y axis it is named as j. In the direction it is of z, it is denoted by k. So xi, xy I, sin y j, x cos z k. Here you see the function xy itself is a scalar point function. Sin y itself is a scalar point function. X cos z is also a scalar point function. So you can write this as phi 1 I plus phi 2 j plus phi 3 k, where phi 1, phi 2, phi 3 are nothing but scalar point functions again. And another example is x plus y into I plus z square k plus x square z k. You can write a number of examples of this kind, which map vectors to vectors, which is called vector point function. If it maps vector to a scalar, it is called scalar point function. So the most important operator, vector operator, is del. Okay, it is denoted by the symbol right? Triangle upside down, it is called as a del. So the operator del actually represent I dou by dou x plus j dou by dou y plus k dou by dou z, right? So this is denoted by the operator del. This operator is denoted by the symbol del, and you can apply del on scalar point functions and vector point functions in a different context. If you apply del on a scalar point function, the result is a vector point function, right? If you apply del on a vector point function, the result is a scalar point function. If you apply del on vector point function, result may be another vector point function. See here, this operator dot is called divergence. It is called dot product. It is called dot product. In this case, this del dot f bar is denoted by divergence of f bar. That means when you apply del on f bar, that means a vector point function, you get a scalar point function, that is divergence. If you apply vector point function, del on a vector point function, and you get a vector point function, that is a curl. In this case, we get a vector point function here, right? So del cross f bar is written as a curl f bar, del dot f bar is written as divergence of f bar, and del f simply, when f is a scalar point function, del f is written as grad f, gradient of f. Gradient of a scalar point function is a vector point function. Divergence of a vector point function is a scalar point function, and the curl of a vector point function is again a vector point function. In vector differentiation, grad f has lot of importance, because the normal to the surface, the normal to the given surface f is in the direction of grad f. Suppose f is the given surface, that means f equal to constant is the given surface, then you find grad f. This is nothing but grad f, right? Grad f, a gradient of f, which is del f. F is a scalar point function. So del f is a vector. Del f is a vector, right? It is denoted by, you denote it by n bar. It is actually the normal. N bar represents, or del f represents the normal to the given surface at the given point P, at any given point P. That means you take a surface, right? You take a point P, whatever point P. So what is the normal? How do you define the normal to the surface? It is actually the perpendicular line to the plane, tangent plane to the tangent plane at the point P to the surface. So at the point P, you take the tangent plane to the surface, then the perpendicular line going away from the surface is the normal to the surface, outward normal, right? Going away outside of the curvature, it is outward normal. So how do you get this normal n bar? It is actually a combination. What is n bar here? Del f, right? Del f. What is del f? I dou f by dou x, j dou f by dou y, plus k dou f by dou z. What is dou f by dou x? Dou f by dou x is change of f, change of the surface, change of f in the direction of x-axis. Dou f by dou x, by keeping y and z as constant. And what is, this is dou f by dou x. Change of f in with respect to change of y is the change of f with respect to change of y in the direction of y-axis, dou f by dou y. And in the direction of z-axis, you have dou f by dou z. If you take a combination of these three with I, j, k, right, that becomes the vector, position vector of dou f by dou x, dou f by dou y, dou f by dou z in a particular direction. That vector is actually n cap or n bar. That vector is denoted by n bar, which is called the normal vector to the given surface. You take any curved surface, the normal is perpendicular to the tangent plane to the surface. Okay, so you are given the surface F, then n bar is in this direction, which is del f. So how do you find the normal to the given surface F? It is just del f. If you find grad f, that is del f, you will get the normal to the given surface F. Then what is del f? Modulus of del f. Modulus of del f is the magnitude of del f in the direction of n bar. In the direction of n bar. That means del f is a vector. It has some length from P to here, from here to here. If it is a vector, it is from here to here. Then it has a length. That length is mod del f. So that is the magnitude of the vector n bar or del f. Then how do you find the directional derivative? What is the concept of directional derivative? The directional derivative is actually the derivative is a del f is the derivative of f in the direction of normal. In the direction of normal. By default, del f is the derivative of f in the direction of normal. But if you want to find the derivative of f in a particular direction, in another particular direction, that is, you take from P to P dash, is another vector, P dash bar is another vector, right, denoted by a bar, right, you denote it by a bar. Then if you want to find the directional derivative of f in this particular direction, then what you have to do is, you have to take the projection of del f on this vector, which means directional derivative is del f dot a bar by mod a bar, which is nothing but the unit vector in the direction of a bar. Unit vector in the direction of a bar. So normal vector to the surface f dot unit vector a cap is unit vector in the direction of a bar. Right. So this value, dot product is a scalar. Dot product is a scalar. This is a vector. This is a vector. Dot product is a scalar. So the value is the directional derivative in the direction of a bar. The direction of specified direction a bar. And it is actually given by mod del f into cos alpha. That means it is actually the resolved part of del f. We have some length del f. Mod del f is the magnitude of del f, and the resolved part of, that means the projection of del f on a bar has a reduced length. That length is given by mod del f multiplied by cos alpha. Right? This is a right angle triangle, and this length is mod del f hypotenuse into mod del f into cos alpha. Right? So mod del f into cos alpha gives the directional derivative of f in the direction of a given vector. And what is mod cos alpha? Mod cos alpha is less than or equal to 1, because cos alpha is bounded by minus 1 and 1. So modulus is less than or equal to 1. So therefore mod cos alpha is always less than or equal to, maximum value is 1, less than or equal to mod del f. So the resolved part is always less than or equal to mod del f. So mod del f is the maximum value or maximum magnitude of the derivative of f. So whenever you are asked to find the maximum directional derivative is always mod del f. The max dd, maximum directional derivative, is mod del f. And other directional derivatives will have a magnitude always less than or equal to mod del f. Less than or equal to mod del f. So this is the concept of directional derivative. And in the next lecture we are going to solve some problems on directional derivative and applications of directional derivative. Okay, thank you.